episode of Beyond the Forecast. I'm Jeff Edmondson. We're going to be talking about NASA Nurture. It's a long acronym. You ready for this? Now here's their website. It's the North American Upstream Feature Resolving Anthropopause Uncertainty Reconnaissance Experiment. Now I had a chance, it's super long, I know. I had a chance to talk to Amin Nehrir. He's the research scientist with this program. They're going to be doing a lot of research and trying to figure out these winter storms that are happening in the upper part of the troposphere. I had a chance to go on board the Gulf Stream at NASA Langley, had a chance to look at some of the equipment. We'll take a look at that now. I'm here at NASA Langley Research Center, and we're here with Amin. We're going to be talking about the Nurture program. What is Nurture?
Nurture is the North American Upstream Feature Resolving Anthropopause Uncertainty Reconnaissance Experiment.
We're going to put like some text at the bottom or something so we can like fill that all out. So we're going to be focusing, and you're doing research on thinking about what's going on in the upper latitudes, winter storms. Tell me more about it.
Right. So this is a meteorological campaign looking to improve the predictability of high latitude winter weather, severe storms. We're going to Goose Bay, Canada with the Gulfstream 3 aircraft outfitted with meteorological instruments, so LiDAR, radar, in situ observations and drop-sons, to target upper level atmospheric dynamics, tropopause polar vortices that bring cold air down to the lower levels. They interact with the jet and they create extreme high impact weather events. Those aren't predicted very well right now, due to sparse observations in the high latitudes and lower information content from satellites. So we place the aircraft strategically around these weather events to get higher information content observations to inform the improvement of models, but also to demonstrate core capability, core technologies for future satellite missions.
So basically this thing is fitted with a bunch of cool meteorology equipment, things to do measurements, drop-sons too?
Correct.
Wow. So we're going to go on board and check it out?
Yeah, let's go.
All right, let's check it out. So when does the campaign start?
We are looking to do a check flight on January 21st, and we depart to Goose Bay January 24th.
Okay. So we're on board the aircraft now. This is the Gulfstream, correct?
This is the NASA Gulfstream 3, correct.
NASA Gulfstream 3, and there's a bunch of different instruments that I'm seeing in front of me, around me. What are we looking at?
Right. So the payload comprises of remote sensing instruments and in situ instruments. On the two forward portals, we have the radar, which gives us information on cloud phase, cloud dynamics. And that tells us how energy is transported through the atmosphere. That's critical for improving our understanding of weather events. On the aft portal, we have a LiDAR. It's analogous to radar, except it uses optical frequencies of light. This one in particular is the HALO instrument. It measures profiles of water vapor, aerosols, so little particulates in the atmosphere that when combined together create clouds. And
so is this, for the LiDAR, is that shooting down, shooting out?
It
How
shoots
does that
down.
work?
So both the radar, so the Cloud Cube radar and the LiDAR shoot down. So as the aircraft moves along, we essentially paint a cross-section of the cloud distributions, the water vapor distributions, the particulate distributions, so that when we're done with the campaign, those data can essentially paint a picture of the atmosphere that we interrogate around the storm. Those data can be assimilated into numerical weather models, and we can understand how the models perform without this data and with the data, and it gives us a sense of the impact of these observations to improve the models, but also how they could be used in the future if these instruments were put in space.
What altitude are you flying at to do this study?
Predominantly we'll be around 41,000 feet, so this is a tropopause polar vortice mission, so we want to get as high into the stratosphere as we can so we can understand the dynamics of how that cold air interacts with the troposphere, and as that cold air descends and interacts with the subtropical jet that comes up, that's where we get the mixing and create the high impact weather in the Northeast corridor.
You were mentioning too that the information that we're gathering from these flights is going to be used in our weather models for assistance and prediction. So I can understand that correctly. You're flying at the tropopause, 40-some thousand feet, 41,000 feet up.
Right.
And we're analyzing those mid-Atlantic cyclones that are starting to form on the synoptic scale. So how long is that flight? How long are we getting this information so then we can send that into that 12Z model run?
Right. So always give a mouse a cookie and they'll ask for more. So scientists will push the envelope of the aircraft. So this aircraft has about a 5.5-hour endurance. So generally when we go do a science mission, we will fly for about 5.5 hours. And that flight pattern will depend on how far away the polar vortice is. So we're looking at Arctic high latitude polar vortices. So a good amount of the time could be transiting to the vortice, and then we'll do a star pattern or a lawnmower pattern across it to get the information on the spatial variability of the atmospheric state, so temperature, pressure, relative humidity, and then we transit back. So we try and optimize the flight plan to get as much science in transit and back and around the storm as physically possible.
Why can't our satellites, like the GOES East or GOES West, do this?
Right. So our satellite capabilities comprise predominantly of infrared and microwave sounders. They are the backbone of our numerical weather prediction, and they provide a wealth of information. The Arctic is a challenging environment because it's very dry. And those infrared satellites that give us the vertical profile information of things like moisture and temperature, they have very little sensitivity to those very dry regions. And by doing so, they can perturb the model in unexpected ways. Building on that, the higher latitudes don't benefit from the dense network of ground radiosonde stations and in situ stations that we have down at the lower latitudes. So those two coupled together can make forecasting at the higher latitudes challenging, and when those poorly forecasted weather events come down and hit the jet, it can create a forecasting challenge for high impact on society. So FAA flight routes and things of that nature. So
so am I wrong in thinking this too? Because we haven't talked about this yet. So obviously the Earth is not a perfect sphere, but it's a sphere. When a satellite is in geostationary orbit, we're looking from the equator up and down.
Sure.
So because in the polar regions, there's more of an angle. Is that a problem too?
Absolutely. So we have our geostationary imagers, which provide a wealth of information. They can give us snapshots very quickly. A lot of information at the higher latitudes come from our polar low Earth orbiters, things like EASI, CRIS, Skiamaki. Skiamaki is an old satellite. Again, those have a lot more those are hyperspectral infrared sounders. They provide a lot more wealth of information. Now, the international community is launching those same capabilities in geostationary orbit, and that is one of the reasons we're actually going out. We're going out to do calibration validation for some of those emerging capabilities in geostationary orbit. So not only are we going out there to interrogate the storms, to get a data set to improve on the models, but we're placing the aircraft around those storms coincident with the satellite observations so that we can help better interpret the observations coming from space, and also at the same time understand how to better develop technologies to overcome those constraints so that the next generation of sounders and LiDAR profilers, radar profilers have the ability to overcome those observational gaps.
So the work that we're doing now can help to improve our forecast in the future.
Absolutely.
That's phenomenal.
Absolutely.
The campaign begins on this Gulfstream 3,
yes,
and then it continues into next year. So this is for 2026.
This is for 2026. It's actually a large international coordinated effort in conjunction with a European campaign called NAUTIC. So Nurture measures the infancy stages, the upstream effects of those high latitude weather storms. The NAUTIC campaign measures the mature stages. So we kind of have this two-component mission where we can see the full life cycle of that evolving storm. In 2027, we're going to go out on the new flagship NASA 777 Airborne Science Lab. That'll allow us to have something like an order of magnitude more instrumentation on that aircraft. So,
there's a lot more space on a 777.
There's
I can actually stand up on a 777.
Absolutely, right. We get to have the microwave instruments, the radar instruments, more LiDAR instruments to get things like winds that help move the weather systems around. So it'll be a more holistic payload.
Any other instruments that are on board here that we haven't talked about yet?
Absolutely. So these were the remote sensing instruments, active remote sensing instruments. Here we have our two operator seats, and back here we have an in situ measurement. So these are trace gases. So flying an in situ trace gas measurement, meaning we actually pull air from the outside of the aircraft. We go through gas analyzers in this rack.
What we're seeing right here.
Yep. So they come down. It brings the air in from the outside of the aircraft, and it goes into a couple instruments in here, gas analyzers. So these gas analyzers give us information on things that are critical to the stratosphere. So ozone, CO, CO2, and measuring these gases gives us a very detailed understanding of the exchange processes from the stratosphere to the troposphere. That's where we get a lot of that cold, dry air that comes down that's very difficult to interpret from the remote sensing instrument. So we have these on board to give us a very accurate depiction of where stratospheric tracers are, so that when we go into the models, we can actually try and recreate that to see, are these small scale dynamics that are difficult to see from space actually being resolved.
Got it. That's fascinating.
Yep.
And I mean, just overall too, it's pretty comfortable in here. I mean, we have the screen set up. Look at these seats. They're nice.
They are
so
very nice.
You're working comfortable too.
Absolutely, right. These are long missions. They're taxing. The researchers are often looking at their instrumentation, but also communicating with the ground. So a lot of this information gets communicated down to the science team on the ground so that we can do real-time optimization. So we send images and real-time data down. People on the ground are looking at it. They look at those geostationary images, and we optimize the flight plan in real time. Of equal importance, and the dropson tube isn't integrated yet, but that blue tube in the back allows us to drop dropsons out of the back. It's analogous to the radiosondes that help with the weather forecast in the lower latitudes. It's a small device that gets shot out of the back of the plane, and it measures temperature, relative humidity, winds. Those data are used for the science for Nurture campaign, but they're also transmitted to the GTS, the Global Transmission System.
Okay.
Of which all of the operational weather centers, so NCEP, ECMWF, all of them, they ingest those data and they assimilate them to improve the forecast and improve the real-time forecasting of weather. And that's really important for the same reason we're going up there. It's a data sparse region. There's no ground measurements, the satellite observations are poor, and so there's an added societal benefit of integrating these observations directly into the operational forecast to get better improved weather.
Are the dropsons similar to the ones that Hurricane Center will use?
They're the exact same ones.
Got it. Same kind of technology, just to study the atmosphere. We're coming from 41,000 feet up, so everything that matters is below you at that point anyway.
Correct.
So you're in a good spot.
Correct. And we fly at high altitudes. It helps us emulate, not only do we capture the full atmosphere and look at the dynamics we're interested in, but it emulates a perspective that we see from space, right? A lot of these instruments have sensitivity with range, and so flying high allows us to see how they perform if we're from a vantage point if we're to put them in space.
Yeah. Anything else you want to mention to me today about Nurture that we haven't talked about yet?
No. This is a unique opportunity to do airborne science and not only have high impact on things that are important to society, so weather forecasts, but advance the next generation of technology so that weather forecasts and predictability in the future are also benefited.
And once again, timeline for the first flight here to get this started.
So we have a check flight on January 21st. Our transit to Goose Bay, Canada is on January 24th, and we will be deployed there until February 20th.
Okay, great. Thank you very much.
Absolutely.
Perfect. Here we're looking at spots in the upper parts. This is where the flight's going to be going. It's going to the upper latitudes around the Earth. Really fascinating stuff. Now, thinking about the atmosphere, it's a very thin layer. So we're going to be doing a lot of research on that. That's what NASA's going to be doing with this research program. And we can think about the atmosphere in a bunch of different spots, and we can look at the different layers of the atmosphere. So let's pull that up. We have the troposphere at the bottom. Even though it's very thin, that goes around the sphere of the Earth. Not technically a sphere, but you get the idea. That's the troposphere. That's where all of our weather happens. Commercial jets, they're flying in that area. When we want to get up to the tropopause, that's the area between the troposphere and the stratosphere. That's that white line, essentially. That's where you can get thunderstorms. To get just about to that point, sometimes they can get a little bit higher. That would be called an overshooting top. So in that situation, that's a really strong and severe thunderstorm when you get that overshooting top to develop. We're not going to talk about that in this episode. We're just going through the layers of the atmosphere. You have the stratosphere. That's 6.2 to 31 miles up. You can get weather balloons that go up all the way into that layer. The mesosphere, 31 miles to 53 miles up. This is pretty cool because there's a bunch of different things that can happen in this area. And here's just a quick overview. We have the sprites, where you get those red lines that sometimes occur in that part of the atmosphere. It's really fascinating to look at images of that. Meteors will be in that area. They'll burn up in that zone. Typically, if they hit the ground, that's called a meteorite. So meteors will be in that mesosphere layer. Then non-tolucent clouds. I remember one time I got a chance to interview astronaut Scott Kelly after his year in space. Remember him and his twin brother Mark Kelly? They were doing a study on how a year in space affects the body. Well, I asked him a question. What do you remember that was unique that you saw from the International Space Station? And he mentioned seeing the non-tolucent clouds. We can get those that sometimes are visible during the twilight hours. So before the sun comes up or after sunset, we can see those. And typically when we'll actually see them are from the exhaust that's left behind from rockets that are launched from Cape Canaveral, because they'll be so high in the atmosphere. We'll see the clouds and the water vapor that's left behind that will create the cloud. Otherwise, you can get those to form too, naturally, again, in the mesosphere. And then you go higher up into the atmosphere, 56 to 300 plus miles up into the atmosphere. There's really not any air anymore up there, but that's where this International Space Station will be. And also satellites will be in that zone too. There still is a little bit of atmospheric drag, so the International Space Station isn't freely spinning and orbiting the Earth. They have to keep raising the altitude a little bit as time goes on to make sure that the altitude remains where it needs to be. So the temperature goes down as you go higher into the troposphere, then it actually goes back up as you go into the stratosphere. Then it goes back down into the mesosphere, but at this point in the thermosphere, there's no air left, so the temperature goes up, but you don't really feel it. Same thing even into the stratosphere too. The air is so thin, you don't feel that temperature anymore. Remember, the temperature is felt because the sun heats the ground, that radiates the heat back up. That heat eventually dissipates the higher you go into the sky. So that's why at the top of Mount Everest, it's always covered in snow. It's always cold, while at sea level, at least thinking of it being at the equator for a best example, it'll be colder. Obviously, in the poles, it'll be colder in those locations because the sun's not as direct for its rays. But that's kind of a fun little feature on how it works. Now, we'll go through the first two layers, and we'll talk about the troposphere a little bit more in detail. That's the surface to 33,000 feet up. That's the lowest layer of the atmosphere. That's where you get 99% of all water vapor and aerosols, the dust, the things that create clouds and precipitation. Most types of clouds form here, except the one that we talked about earlier, the overshooting top. Those form a little bit higher. This is basically where our weather occurs. Temperature and pressure decreases with altitude. We talked about that. And this is also where the majority of the atmospheric mass exists. It's all in that lowest level and lowest layer of the atmosphere, the troposphere. Tropopause, that's around 36,000 feet. You can get commercial jets to be hanging around right there. So that's when you're hanging out in the zone between the troposphere and the stratosphere, kind of riding the line a little bit. Can't really tell the difference, but that's kind of a fun little fact that you're doing. That's where temperatures are consistent with increasing altitude. Temperatures are usually around, it's super cold in Fahrenheit, 60 to 76 degrees below 0 Fahrenheit. It acts as a ceiling essentially for those thunderstorms. So you'll get those anvils to form out, to spread out from a thunderstorm. Those big, high, wispy clouds that'll extend far out from a thunderstorm. But if there's enough upward motion that can break through the tropopause and you get that overshooting top, so it looks like you'll have a cumulus cloud, the kind of rigid edge on top of the intense updraft of a thunderstorm, you'll get that to form on top of a very strong thunderstorm. That's where the aircrafts will fly. That's where the jet stream and turbulence is also hanging out. One more layer here. We'll go into the stratosphere. Weather balloons keep going into that area. That's the second layer of the atmosphere, very dry air, stable air. You can sometimes get, and it's not mentioned on this graphic, but you can sometimes get volcanic ash that'll go up into the stratosphere. The problem with that is you won't get a thunderstorm that'll roll through, that'll rain it out, that'll clean it out, because the thunderstorms are hanging out in the troposphere. They're hanging out down below. So if you get something that goes into the stratosphere, it could be staying there for a very long time. So a huge eruption from a volcano, that can spread across the stratosphere and keep that area covered or at least concentrated with that volcanic ash, reducing the amount of sunlight that gets down to the surface and cooling the temperatures maybe for the Earth. That's happened before with volcanic storms, or volcanic eruptions, I should say, and it could happen again. We're going to take a little break here. We're going to go through the rest of the layers of the atmosphere, maybe even touch on a little bit about the magnetosphere too, all coming up on the special edition episode of Beyond the Forecast. we've been talking about the atmosphere, the layers in our atmosphere. It's such a cool place, and it's the reason why we can live on Earth. Now, there are other planets in the solar system that have atmospheres. We can think of, just off the top of my head, we can think of, in terms of planets, we have Venus that we know that has a very thick and dense atmosphere with really thick clouds. Acid rain falls on that planet. It's super hot. So it's a greenhouse effect that went out of control. It's just a little too close to the sun, and it's a little hot and very dense of an atmosphere. Mars has an atmosphere as well, much thinner. We can use it to slow down our spacecraft, and we have used that before for our Mars rovers, Spirit and Opportunity, also Curiosity and Perseverance. They have used air braking through the atmosphere. It's not a perfect way to slow down. It can help you a little bit. It doesn't help you all the way like it does on Earth, where a parachute can slow you down to a safe landing speed. Other gas giants, Jupiter, of course it has an atmosphere. It's a big ball of gas. Saturn, Uranus, Neptune, those planets have atmospheres as well. And even some of their moons have atmospheres too. We'll be doing more research on that as we continue on. But let's not talk so much about all the other planets. Let's stick back to what's going on Earth. So we talked about the stratosphere. We have the mesosphere as well. This is where sounding rockets launched from Wallops Flight Facility and other launch facilities that study the upper parts of the atmosphere will go into. So we're looking at the third layer where most of the meteors vaporize, higher concentration of metal or really powerful and large meteors, or maybe some that are moving at the correct speed, not too fast, maybe not too slow, can survive that push and make it all the way down to the ground. Temperatures decrease with altitude in the mesosphere. Coldest temperatures in the atmosphere, we're down to 130 degrees below zero. So super cool. The upper boundary, the mesopause. The lower boundary, the stratopause. And then finally, the atmosphere that matters the most for the aurora borealis, the northern lights. That's in the thermosphere. That's also the areas where we have the magnetosphere, where the charged particles from the sun will travel through the magnetopause. It'll hit that. A lot of different things going on in terms of space weather will be in this sector as well. The ionosphere, there's so many different topics. Back to the thermosphere, the layer below the exosphere, considered essentially outer space, where the International Space Stations and satellites orbit. Very low density in this area, where you can have atomic oxygen, nitrogen, and helium in this area. Temperature increases with altitude, and the temperature is strongly influenced by solar activity. Really cool stuff. That's why on our spacecraft, you can have the sunlit side be super, super hot, and then the other side is super cold. The upper boundary, the thermopause, and then below that is the mesopause. So a lot of fun things about the atmosphere. Again, we'll look back to this image from the International Space Station. It gives you a good idea on what the atmosphere is and what it looks like. All the cool stuff is happening down at the ground. I want to give a shout out to NASA Langley Research Center once again. Thanks for having me out to talk about the Nurture program, as we're going to study more and more about the upper latitudes and how our weather and winter weather develops here across America and North America too, the whole continent. Fun stuff. We're going to continue to have more things coming from NASA, more things here on Beyond the Forecast. Thanks again for watching this episode of Beyond the Forecast. This was a fun one. We'll see you next time